Okay, I'm gonna go live.
Great. Hello, everyone. Welcome. Still lots of people filing in, so we're just going to wait a couple minutes before we get started. Alrighty. Hello, everyone. Welcome. Welcome to Café Scientifique from all of us here at the SFU Faculty of Science. If you're one of our regulars, thank you for joining us again. And if you're new, thank you for joining us for the first time. It's always nice to see a mix of familiar and new names at these events. My name is Stevie Benish, and I'm the acting manager for outreach and engagement with the Faculty of Science, and I'm going to be your host this evening. For those who don't know, Café Scientifique is the Faculty of Science public seminar series where our faculty presenters share their current scientific research and what its impact on our local communities or larger society is. And today is our last cafe for this calendar year, but we're looking forward to bringing back more speakers for next term and seeing you all again in 2025. We typically have about 6 to 8 presentations a year, and they're all virtual, and they're also all recorded. So you can view them from our website if you missed something, or if you would like to share the presentation with a friend or family member. So we'd love to hear from you. So please stay in touch after this event. Um, you'll get a link in your follow-up email, so please feel free to reach out at any time. And you can also join our mailing list to receive any updates on our upcoming events. So before we get started, I'd just like to start us off with a land acknowledgement. So here at SFU Burnaby, we are privileged to gather on the unceded and ancestral lands of the Musqueam, Squamish, Tsleil-Waututh, and Coquitlam peoples. We thank them for having cared for and been stewards of these lands since long before our times. And we look forward to working with them in partnership and continuing to build and grow our communities together. If you know whose land you are currently on, I would encourage you at this time to just take a moment to reflect on that. And if you don't know whose territory you're currently on, a great resource for more information on that is native-land.com. And there you can familiarize yourself with the Indigenous people whose land you live and work on. So, few rules, very short, pretty simple. So, uh, how it's going to work is we're going to have our wonderful talk and then there'll be a Q&A period. So if you have any questions, please type them in the Q&A box and we'll try and do our best to get everyone's questions at the end of the presentation. But please feel free to ask as much as you want. Anything we don't get to, we will reach out after email. The chat will be turned off during the presentation. So once again, just use that Q&A box. There is a live transcript available for your convenience. And once again, just a note that this is being recorded and will be shared on our website. Alrighty, so now I get to welcome who we are all here to see tonight. I am so pleased to be able to introduce Dr. Samira Siahrostami, who is an associate professor in our chemistry department and a Tier 2 Canada Research Chair in modeling electrochemical reactions. Her research focuses on digital and computational catalysts, specifically targeting its application in advancing clean energy technologies such as fuel cells, electrolyzers, and batteries, and key components for establishing a sustainable energy economy. Her research is also, her long list of accomplishments includes many things. I don't think I have time to list them all, but just a couple highlights is the American Chemical Society Women at the Forefront of Energy Research, the Tom Ziegler Award from the Canadian Society of Chemistry, and the Waterloo Institute for Nanotechnology Rising Star Award. So tonight, her talk will cover solutions that digital chemistry can offer to global challenges, such as the growing demand for energy and the need for environmentally friendly technologies. So we're very excited to have you here with us tonight, and I'll pass it over to you. Thank you so much.
Thank you so much, Stevie. It's an honor to present my research today. And let me just share my screen here. And let me know if you see my slides on full screen. Okay.
Yep, they look great.
All set? Perfect. Yeah, so thank you again for the opportunity. It's a pleasure for me to give this seminar today, and hopefully I can explain to you what we are doing at SFU. It's a wonderful institution with a really great research facility, and we are honored and excited to work on this area of clean energy technologies and developing materials for clean energy technologies. So I'm hoping to show you what we can do to solve some of our grand challenges with energy and environment. But before I address that, I'd like to start with this slide, which shows that we're currently living in an era of fossil fuels. And so shown here is the total world primary energy supply, which is in 2023. And so as you can see here, a lot of our energy today comes from fossil fuels. And so we are not only relying on fossil fuels for energy supply, such as electricity generation or transportation, we also heavily rely on fossil fuels for making our materials, pharmaceuticals, and fertilizers, and so on. And of course, there's an obvious reason behind it. Fossil fuels are a great source of energy. They have high energy density. And so shown here is an example of where, for example, gasoline or diesel, which we are commonly using in our daily transportation, have their energy density. So this is showing energy density per volume and as a function of energy density per weight. And so these two commonly known fossil fuels are right at the right corner of this graph, which shows that they have both high energy density per volume and high energy density per weight. So note that batteries are right in the corner of this graph. which means that we have a long way to go to get to this high energy density and desired region for high energy density. What does it mean? So what this means is that, for example, if you take, I'm sorry, just a second. Sorry, the light goes off time to time. Okay, so what this means is that if you take 1 gallon of gasoline, you can keep your TV on for 35 straight days. And if you can think of a size of a battery that can do this for us, would be a gigantic battery, I guess. The other example that I can give you is if you take 13 gallons of gasoline and put it in your tank of your car, you can drive it 400 miles. And so with today's technologies, the batteries, we can't do that just yet. So we still have work to do and more research to be done in terms of developing catalyst materials and developing battery materials to get to this target and meet our demand and energy demand we have in our society. So of course, the fossil fuels are a great source of energy, but it comes with its own downsides. For example, we have limited supply of crude oil. As this graph shows, the consumption of crude oil has been increasing over the years, and it continues to increase. But the future discovery of the crude oil is decreasing, and as we extract more and more oil, we will have less and less chances to extract the easy oil, because then we have to go deeper and deeper, and that makes it more difficult to extract the oil, even if we have reserves. And of course, the other side of this, the downside of the fossil fuels, is the greenhouse gas emission. As you all have seen, the CO2 concentration in the atmosphere is increasing when we are consuming fossil fuels. And so this is a report from UN. The greenhouse gas reached the record observed level in 2023, which is 420 ppm. Okay, so what does it? The impact of these greenhouse gases are? One impact is, of course, on global warming, and this is showing the annual global mean temperature. And so the current global warming is about 1.3 degrees C, which is higher than the average of the last 10 years. And so it's kind of sounding the alarm because it's getting warmer faster than what was expected, and so we have to take actions. The other impact of greenhouse gases and global warming is, of course, melting the glaciers, and this results in rising the sea levels. So here's shown, what this is showing here is the glacier loss over the years, and this is showing the sea level rise. So these are all actual data that are reported in UN recent report on the state of climate change. And so all of these are actually getting us to the point that we really need to take actions on different, whatever we can. So one of the few of the impacts of the climate change that we have seen frequently, of course, warming ocean temperature is one of them, which results in rising sea levels. We have frequently seen wildfires in BC, and this continues to happen, unfortunately. And of course, food insecurity is another downside of the climate change. So actions are needed to be taken. And so UN Sustainable Development Goals, UN monitors these impacts and these effects. And this was these Sustainable Development Goals were developed back in 2015. And so the goal was, these are 17 goals that aim to address these current challenges, and hopefully we can protect our global and nature and world for the possible 9 million people who will appear on Earth in 2050. Okay, so there has been some positive actions, and so, for example, renewable electricity and using renewable sources to generate electricity is one of them. And Canada is actually on the forefront of these action and has been taking. We are fortunate to live in this country, that this country has taken good actions along this. For example, in Canada, we are generating a major portion of our electricity using hydro, which is roughly around 63%. And so there are other sources of renewable electricity, and depends on where we live in the world. So in Canada, we have the privilege of hydropower. That's why we rely mostly on using hydro for generating electricity. And so if you want to know where we are in terms of the global low emitting electricity production, so this is showing 17 developing countries. And so we are number 5 out of these 17. There's still room to improve, but we are walking toward the right pathway. Now, if you think about global cost of electricity, again, another really good and positive step, you see that the global cost of electricity using renewable sources has dropped quite a lot. For example, here we have all these various different renewable energy sources, and shown here is the cost of producing electricity using various sources. The gray box here, or gray bar, shows the fossil fuel cost range. So ideally, we want these renewable sources to generate electricity with the cost lower than the fossil fuel cost range. And so you can see that a lot of these renewable sources now, and even since 2020, are now cheaper for production of electricity. And that is a very good sign. So this means that switching to renewable electricity generation is a very good option and affordable technology for people. Now, what can we do with these cheap electrons? Can we use them toward something more useful, apart from, for example, using electricity in our home? One of the other ways that helps to reduce carbon emission is to store this renewable electricity, which are now cheaper than fossil fuel electricity-based generation. And so one way to store this electricity is to electrify our batteries. For example, we can electrify our vehicles that are based on battery technology, or we can use a grid energy storage system, so we can store this renewable electricity for the time that the sun is not shining, for example, during the night, or the wind, for example, is not blowing, so we can use that as a backup power. The other way to think about using this renewable electricity is to store this renewable electricity in the form of chemical bonds. And so that's what we call synthetic fuel. So imagine you can transform the energy of solar energy into chemical bonds that you need for society. So for example, you can make ethanol, methanol, or hydrogen using renewable electricity. And for that to happen, we need electrochemical reactions or electrochemical devices, such as electrolyzers and fuel cells. So this is the goal of my research. In my group, we are trying to synthesize electrochemically synthesized fuels and chemicals. And the electricity ideally is coming from renewable sources, so the whole technology is clean. So taking hydrogen as an example, hydrogen is a key player in reducing carbon footprint. And so our government's actually taking really good action in implementing hydrogen technologies into our society. And so one of the examples is that, for example, we can electrolyze water to generate hydrogen instead of using fossil fuels to generate hydrogen. That would be a clean technology to make hydrogen. And then this hydrogen technology using electrochemical or electrolyzing water using electrochemical reaction uses the renewable electricity. So then this clean hydrogen can be used for upgrading other chemicals, or it can be used, for example, to drive our cars that have fuel cell technology. So I will talk about this in more detail. This technology uses hydrogen as a fuel, and it only generates water. So it's a clean technology that I will talk about later. So if we put all of these together, we can hope to have a sustainable energy landscape in which we generate our electricity using renewable sources. And we use this renewable energy or electricity to convert low-value chemicals that they don't have any chemical value for our energy systems, and convert them to higher value chemicals. So for example, taking water and electrolyze it using an electrolyzer, we can make hydrogen, or taking, for example, CO2, capturing CO2 and converting it to hydrocarbons and fuels. We can also think about converting nitrogen to ammonia, which is a key chemical for fertilizers. So in order to do that, we need an electrochemical process. And at the heart of this electrochemical process sits a catalyst or an electrocatalyst that we code on the electrode surface of the electrochemical device. And so what is a catalyst? Catalyst is a material that converts certain reactants to products without being consumed in the process. And so a very good example of that is if you have a reaction that starts from reactants to product, without catalyst, you have to spend more energy to convert this reactant to products. But with catalyst, you will require less energy input, which means your process is more efficient. And so catalysts are very important materials in our society, in our industry, and they have been used for manufacturing a lot of materials. And so, for example, if we have a reactor, at the heart of this reactor sits a catalyst, and these catalysts are made out of either nanoparticles or some form of powder shaped catalyst. And so at the core of these nanoparticles is the atomic scale. That's where the reaction is happening. So you have these reactants that sit on the catalyst surface, make bond or break bond, and produce the products. Yeah, so as I mentioned, catalysts are everywhere. They are used to manufacture more than 90% of our chemicals and fuels. For example, for pharmaceuticals, for gasoline production, plastic, and fertilizer. For all of these processes, we need catalyst materials. And so if you look at the global market of catalysts, it's increasing. And so this is today the market value, and it's expected to increase more over the next several years. And so this is just showing how much our society needs catalyst material. So this is a very important area of research, and we need catalysts that are more efficient so we can make materials more sustainably and products more sustainably. So here's an example. One of the examples of a catalytic process that we rely on heavily, it's the ammonia synthesis process, which is today produced through Haber-Bosch process. This is in a large-scale facility, and the process was invented by Fritz Haber and Carl Bosch around 1900. It requires high pressure and temperature, so you can imagine it's not a carbon-free or free carbon footprint process, but there are actions taken into making it more sustainable or find other ways of making ammonia synthesis that is more sustainable. But the key point here is that this is a very important reaction for us. And this is showing, this graph on the right shows the relation or the dependence of population growth on ammonia synthesis. So this is around 1910, where the Haber-Bosch process was industrialized. And so as you can see, the ammonia production, as the ammonia production increased, the population growth increased as well, because people could now have more access to food, and fertilizers were produced all over the world. Okay, so how do we develop catalysts, and how do we know a catalyst is a good, is the appropriate and the best catalyst material for the process? So there are several ways to develop catalyst materials. There has been a lot of research and progress in terms of how do we actually tailor the catalytic property to address and produce the product that we need for a reaction, for a certain reaction. So this is showing a diverse strategies for catalyst development. There are in one direction, you can increase the number of sites that the reaction is happening on. And this could be by nanostructuring, making different nanostructure materials, or by supporting it on different substrates. You can also think about the shape of the nanoparticles affecting the catalytic properties, and so on. So there has been a lot of effort in terms of making these catalyst materials to make them more efficient for a catalytic reaction. Now, one thing that is a problem here is the timeline for catalyst development. So if you think about trying all these different strategies, and materials space is actually huge. So taking various different types of catalyst materials and doing all these strategies in terms of like nanostructuring or making different nanoparticles and so on, it takes years to develop a catalyst that works for a reaction, and also for the process to be commercialized. For example, with today's technology, the process of discovering a new catalyst, it takes 1 to 5 years at least. And the catalyst that is discovered in this phase needs to be optimized and characterized. That also takes at least 6 months to 2 years. And we also need to test and commercialize this. That's another additional 1 to 5 years. So in fact, the discovery of a new material, catalyst material, takes 3 to 10 years in terms of timeline. Now, the question is, can we do better? And so here is when the computational and digital chemistry can help. So instead of spending a lot of effort and time and money into making materials and synthesizing them and testing them and optimizing them, we can do all of these in our supercomputers or our using high performance computing technologies. And so in fact, we can use this digital chemistry to boost the process of catalyst discovery and accelerate the catalyst discovery to 1 to 2 years instead of 5 to 7 years that we see here in the experimental discovery. Now, what do we exactly do here? So in silico catalyst design or digital chemistry is the process that you screen a lot of different catalyst materials and get their properties in using computer simulation. And so the catalyst design using digital chemistry has basically two different classes. The first class, which is gives us the fundamental understanding on the catalytic properties, uses quantum chemistry calculations. And using this quantum chemistry calculations, you can generate a lot of data that can be trained for accelerating catalyst discovery using AI and machine learning. And so once we do this using computational technologies, then we come up with a catalyst candidate or a material that works for the reaction. And then we can pass it to the experimental researchers to test, synthesize, and test this catalyst material and validate that. So here's an example that you can probably relate to. That's how this is done in computational chemistry. So for the example of ammonia synthesis, we need to model the reaction on the catalyst surface. This is taking nitrogen and hydrogen that come to the surface. They break bond and they form bond with nitrogen one at a time. So as you can see, this reaction, which the whole reaction is nitrogen plus hydrogen giving ammonia, it has many different elementary steps or a lot of other small steps that are involved to run this reaction as a whole. And so the interaction of each of these species that are formed during these reactions are actually critical in terms of identifying the catalytic properties. And so the strength of the interaction of these species with the surface is what it defines the catalytic properties. And so experimentally, it is very difficult to capture the interaction of all of these species because these are short-lived, short-life intermediates or species that are formed during the reaction, and they will be removed from the surface as soon as they form bond again. So one thing that the quantum mechanical calculations can help is to get the interaction energies or the absorption energies of these different intermediates with the surface of the catalyst. And so if we do that across various different catalyst surfaces, we will be able to identify the most optimum catalyst based on what we call Sabatier principle, which is basically an activity volcano shape map. And it maps the bond strength of these species or intermediates on the catalyst surface. And so what Sabatier principle says is that the maximum activity or the optimum catalyst that you're looking for has to be has to bind these intermediates not too strongly and not too weakly. For example, if the intermediates are bound to the surface very strongly, you will have a low rate for the reaction. So then you have a strong interaction with the intermediates. The intermediates come to the surface, they break bond, and they don't leave the surface. So they will not be able to make product. On the other side of the thing, we have catalyst surfaces that have weak interaction with the species of the reaction or intermediates of the reaction. And that also results in a low rate because the reactants come to the surface, but they bind very weakly to the surface. So they can't really proceed to the final product. And so the optimum or sweet spot of activity comes on the catalyst surfaces that bind intermediates not too strongly and nor too weakly. And that allows the reaction to proceed. The reactants come to the surface, make bond, create bond, and leave the surface. So that's a principle that has been known for years. What computational and quantum mechanical calculation can do is to actually feel these the points on this map and identify that catalyst materials based on the bonding strength of those intermediates to the surface. So here is how this looks like if you do the quantum mechanical calculations for ammonia synthesis. So this is combining nitrogen and hydrogen to form ammonia, going through all these possible intermediates that can be formed throughout the reaction. And so you can map out the free energy of all of these different species and identify the reaction mechanism and identify where there are bottlenecks and which of these steps hinder the progress of the process over a given catalyst surface. And so this is how quantum mechanical calculations can help us. With these techniques, we can map the mechanism of the reaction and identify the optimum catalyst material. Now, what is the basis of quantum mechanical calculations? And so to understand that, we need to go back in 1800 to 1900 when Schrödinger suggested the Schrödinger equation. By solving this equation, you can get the energy of the system. And so by knowing the energy of the system, you can map the energy diagram and reaction mechanism of the reaction. And it's easy for simple atoms like hydrogen. You can solve the Schrödinger equation, which has all these interactions of the electron and nucleus on each certain atoms. But it becomes really difficult when you have multi-atomic systems, like, for example, platinum. And not to mention when you have nanoparticle of different elements, that means you have many, many electrons in the system. That makes it very difficult to solve Schrödinger equation. And in these cases, there's another method in quantum mechanical calculations, which is called density functional theory. And in this approach allows to take, instead of taking the electron-electron interaction on each atoms and elements, we can imagine that we have the whole electron density interacting with the effective potential. So that simplifies the problem, and that has been a very successful approach to identify the energy of many electron systems. And this is the approach we are using in our research for obtaining the energy of the system and interactions of the intermediates with the catalyst surface. And so that is using density functional theory, we can establish structure-activity relationship for any given catalyst surfaces. And so that is the common practice in my group. We are running these calculations to identify the reaction mechanism for various catalyst surfaces. We can identify which catalyst is better for a reaction. And we can identify if there are any correlations between reaction intermediates to kind of reduce the dimensionality of the problem. And we establish these volcano activity relationships that allows us to screen various catalyst materials and identify the most optimum catalyst for a reaction. We also look into the electronic structure properties to understand why a catalyst works better for a reaction and learn from it so we can design better materials. So here's different directions of research in my group. We are working on producing hydrogen using renewable sources. So here is an electrochemical device that electrolyzes water to oxygen or electrolyzes water to hydrogen peroxide. And so on the other side of this device, you can generate hydrogen, because by electrolyzing water, you can produce protons and electrons, and then you can collect them on the other side of this electrochemical device to make hydrogen. We can also use hydrogen sulfide and electrolyze hydrogen sulfide, which is a waste chemical, and extract hydrogen from this chemical. And that's also an interesting research direction that we are pursuing. We can also use the other direction in my group is to utilize hydrogen. So imagine you made hydrogen using renewable technology. Now, what can we do with this hydrogen? We can put it into fuel cell to generate electricity. So here we have, we are oxidizing hydrogen, making protons and electrons that allows us to reduce oxygen to make water. And upon this reaction, you can generate electricity. You can also use hydrogen to upgrade chemicals. For example, you can convert nitrate to ammonia using this renewable hydrogen, or you can reduce CO2 to valuable chemicals like methanol or ethylene and so on. So I want to give you two examples today, just for the interest of the time. The first example, as we talked a lot about hydrogen, focuses on designing catalysts for fuel cells. And so this was a project that I started when I was an associate staff scientist at Stanford University. We collaborated with Toyota Research Institute to accelerate catalyst material discovery for fuel cell application. And so fuel cells are, again, a clean technology that we can use in our transport sector. So this technology is also based on electrochemical device, but instead of battery, they're using fuel cells, which consume hydrogen as a fuel. So just to give you more detail about fuel cell, this is showing a schematic of fuel cell structure, which is an electrochemical device. And like any electrochemical device, it has an anode, counterpart, and cathode. In the anode, we have hydrogen, which is oxidized. It forms protons and electrons. Protons pass through the membrane, and electrons pass through this external wire to reduce oxygen in the cathode to water. So in fact, the output of this fuel cell is water. It reduces oxygen, so it's a very clean technology, zero carbon footprint. Now, the challenge we have is that traditionally, fuel cells are using platinum-based catalysts for reducing oxygen to water. And generally, this is the process that is a bottleneck for fuel cell efficiency. And developing a catalyst material that does this oxygen reduction reaction more efficiently will result in a more efficient fuel cell. We also want to depart from using platinum-based catalysts, which makes this technology unaffordable to public. So that's the main goal of my research, or the goal of discovering catalysts for fuel cell production. So we want to find a better catalyst for this oxygen reduction reaction, which is shown here. So in order to design a better catalyst, we need to understand the reaction first. And so similar to ammonia synthesis, we have this overall reaction, which is reduction of oxygen to water. But of course, this reaction goes through a sequence of elementary steps, and it forms various species along the way to get to the product. For example, in this case, we have 4 different elementary steps that are forming 3 different intermediates, which are OH, oxygen, and OH. And so you can also follow this on this schematic here. The oxygen molecules need to be absorbed for example, at the platinum surface. And it takes the proton and electron, protons from the solution and electron from the electrode surface. It forms the first intermediate, which is OOH. And then it forms the second intermediate, which is oxygen. It releases 1 water molecule here, and then it reduces back again to OH and water. So again, using the computational calculations or quantum mechanical calculations, we can obtain and calculate the energy of interaction of each of these intermediates with the catalyst surface. And this is given in the example of platinum. Using this analysis, we can identify the intermediates that hinder the reaction to proceed. And we can also identify another metric, which is kind of describing the activity of reaction. And this is coming from computational analysis. And it can be compared to the experimental results. This is called the calculated limiting potential. And again, just using calculations, we can obtain this metric. So with these 3 metrics, which are the bottlenecks of the reaction, is formation of OOH and formation of OH, as well as this calculated limiting potential, we can go ahead and do a massive catalyst screening. And so we can identify other catalyst materials that are more efficient than platinum, or at least better alternative or more cost-effective alternative to platinum. So we have worked on various different directions, various different catalyst materials. Again, the catalyst material space is huge, and using computational analysis will help us to do this a screening of these materials virtually, so we don't have to actually synthesize them and test them experimentally. And then finally, once we obtain the most proper or suitable catalyst, then we can pass it to experimental groups for verification and testing. Okay, that brings me to my second example, which is electrochemical synthesis of hydrogen peroxide. And so we are interested in making hydrogen peroxide for solar distributed water treatment system. And I'm just going to show you a few advantages of hydrogen peroxide in this slide. Hydrogen peroxide is one of the 100 top most important chemicals that we have in the world. And it has various applications in different industrial processes. The annual production of this chemical is around 5 million tons. And it has, again, various applications in paper bleaching, chemical synthesis, textile, and so on. It is also a promising chemical to use for energy as an alternative clean fuel. So shown here is the density of variety of these emerging fuels for clean technologies, including hydrogen and ammonia. And as you can see, hydrogen peroxide has the highest energy density, so it makes it very suitable as a clean alternative and clean fuel for future use. Now, industrially, hydrogen peroxide is synthesized through anthraquinone process. It is an energy-demanding process that requires large infrastructures and facilities. And then hydrogen peroxide that is synthesized need to be transported to the place of use, which means we have to. This means the carbon emission and GHG emission. This process also applies a lot of organic solvents to produce hydrogen peroxide. So we need to make this more sustainable. And speaking of more sustainable societies and industries, one way to do that is going through electrosynthesis process. So electrochemical processes are clean, they're easily adaptable. You can use them at the place of use, so you don't need to transport hydrogen peroxide to the place of use. There's no organic solvent or molecules required. You can reduce oxygen to hydrogen peroxide without the use of solvents, and no need to transport. So this is how this looks like. So if, speaking of electrochemical synthesis procedures or processes, you can use fuel cell to reduce oxygen to hydrogen peroxide. And remember, we just talked about reducing oxygen to water for high efficient fuel cells. Here we want to reduce oxygen to hydrogen peroxide, again, using the hydrogen. And so this process is a 2-electron proton process, so it has less elementary steps if you think about the reaction mechanism, and it competes with the 4-electron process, which reduces oxygen to water. So in fact, it is very important to design a catalyst that selectively forms hydrogen peroxide if the goal is to synthesize hydrogen peroxide. We can also use an electrolyzer to produce hydrogen peroxide. So in this process, we can electrolyze water to hydrogen peroxide, and this is also a 2-electron process, but it also competes with 4-electron oxidation process, which makes oxygen, and it makes more proton and electron. But in fact, again, if we want to make hydrogen peroxide, we need a suitable catalyst to drive this reaction rather than driving the other possible water oxidation processes. So in my group, we're working on both of these two directions, trying to optimize these devices for producing hydrogen peroxide. And again, for the interest of the time, and because I talked about fuel cell, I'll focus on the fuel cell direction. And so if you think about the reaction of the intermediates with the catalyst surface in the 4-electron transfer step, where we make water in the fuel cell, we have 4 elementary steps that we talked about. Now, in the hydrogen peroxide production, which we know now is a 2-electron process, we only have two steps that are involved. And so moving from this step onward, it will determine the product of the reaction. So as soon as the first intermediate is formed in both of these two pathways, which is common between them, and it's called OOH intermediate, the next step, if it breaks this oxygen-oxygen bond, it will give us water. And if we can somehow protect this oxygen-oxygen bond using a proper catalyst surface, you can make hydrogen peroxide. So what this means is that selectivity is a challenge. And for the oxygen reduction catalyst to make hydrogen peroxide, we need to identify a metric that defines a selectivity. So again, experimentally, it is very difficult because we can't measure these interactions experimentally with our techniques today, hopefully in the future. But with the computational methodology, we can get this information. And so this is an example of the work we've done quite some years ago. We designed active sites using atomic scale configuration of these elements. And so in this idea, we kind of isolated the sites that bind oxygen with atoms that don't bind oxygen. And that's why it is called isolated active site. So we kind of isolated the active site with elements that don't bind oxygen. And so the way it helps us is that once oxygen binds to this active element, the next step is reducing it to hydrogen peroxide, simply because the site that is sitting next to it is not willing to absorb oxygen. So then the breaking of oxygen-oxygen bond is not an option on these catalysts. And so these are all active sites that have been, so this was the idea that we had, and we looked at alloys or real alloy structures that have this property. And so here are some of the example of structures that we tested. And so these are all possible combinations of elements that give us these isolated active sites. And then we did this usual volcano relationships that allows us to pinpoint and identify the optimum catalyst. And so this was through a computational screening. We identified this 4 or 5 candidates that were promising, and they were tested experimentally and verified, and then commercialized. And now there's a company in Denmark that uses this technology for producing hydrogen peroxide. We also worked a lot on other alternative catalyst materials that are easier to synthesize and be commercialized. And speaking of that, we worked a lot on carbon-based materials. We designed active sites in carbon-based materials by modifying the electronic structure of carbon structures. And these are various ways that we pursued to design the active sites and modify the electronic structure of the carbon structures. We collaborated a lot with the experimental groups around the world to make sure to synthesize these materials, to test them, and a few of these were commercialized out of this research that we have done. So again, what is the application? If we can make hydrogen peroxide using a fuel cell, we can use it on site for water treatment because hydrogen peroxide is a green chemical oxidant, and it disinfects water, and it only produces oxygen and water when it does the disinfection and water treatment. And so this has been tested. This is technology that was developed in the lab, and then it was commercialized. There's now a company in Denmark that produces this fridge-size electrolyzers that generate hydrogen peroxide for water treatment in agricultural field. And this is very helpful for overcoming the water crisis, especially in in many parts of the world, people lack access to clean drinking water. So if we can make, not everywhere they have access to clean drinking water and centralized facilities to do clean drinking water. And so this technology can help to access clean water in remote areas. Okay, so with that, I hope I have been able to convince you that in silico catalyst design, using computational and quantum chemistry can help to facilitate and accelerate catalyst discovery. And this is really important for developing technologies that we require for our sustainable energy and sustainable landscape and society. And so with that, I can finish, and I hope if you have any questions or anything, just let me know. I'll be happy to answer.
Thank you so much, Samira, for that. I love these. I always feel like I learn so much. And it's always incredible the exciting research that's being done at SFU. Alrighty, so yeah, just a reminder, anyone, if you do have questions, please just type them in that Q&A function, and we will get started right away with the first one. So our first question here says, can you give some examples on the cost of various catalyst materials and how this is factored or optimized into their practical application?
Yeah, that's a very good question. It depends. Usually, if the catalyst itself is made out of an expensive metal like platinum or iridium, of course, part of the cost goes to actually making this catalyst material or actually purchasing the catalyst itself. But then making it proper or suitable for a catalytic reaction itself, it also requires further processing of that material, making a nanoparticle out of it, or manufacturing it further, and so on. So it all depends on where you want to go. So in the commercialization process, there are many different metrics that come into play. And so that's why we want to switch to catalyst materials that are earth abundant and safe and also cost effective, because eventually that plays a major role in the end cost of the material.
Wonderful. Thank you so much. And then another question here is, how accurate are the computational methods in predicting the catalyst properties?
Yeah, thank you so much for that question. I actually had a slide on that. So we generally, the density functional theory calculations have different approaches. If you want to have really high accuracy on your results, you can choose a functional or a method that gives you that high accuracy. But there are also versions that give you reasonable accuracy, and that helps to also kind of trust your results are accurate enough. But if you increase the accuracy of the method of calculation, that means you have to spend more time, computational hours, and it doesn't come for free, although we want to think of it as a free method, but computational hours also expensive. Of course, much less expensive than experimental tools and techniques for synthesizing and characterizing materials. But it also is costly if we increase the accuracy of the method. That means we have to spend more computational hours.
Wonderful, thank you. Look, another question here. What drew you into digital chemistry as a field? I think it's something that, I don't know, maybe a lot of people in the general public don't know that much about or think about, but yeah, I'd love to hear kind of how you got into this field.
That's a very good point. So I was an undergraduate student in chemistry, and I passed all different chemistry courses and chemistry labs. And it was until I think my third or fourth year, which I took a quantum chemistry course, and I just loved this course and the material, and I thought this is something I want to do for the rest of my life.
I love that. That's, yeah, that's amazing. Okay, another great question here. What is the expected lifetime of a catalyst, and can the catalyst be reused?
That's a very good question. So again, it depends on the reaction, and it depends on the process, the catalytic process. Usually we want to extend the lifetime of the catalyst because especially if it's made out of like expensive metals, we don't want to lose them. But again, it depends on the reaction and the process. For a lot of these electrochemical processes, because the environment, the electrochemical environment is harsh, it usually has high electrode potentials and high or acidic medium. The lifetime of the catalysts are shorter, and that is also an area of research that to improve the lifetime of the catalyst, maybe coat it with something to kind of extend its durability and so on. But again, this is also very dependent on the reaction or the process of interest. A lot of the industrial processes have catalysts that survive maybe years, but then they also come in a larger and bulk portion. So they have to replace the catalytic batch. And of course, they want to keep everything, the catalyst untouched. But when the reaction happens, the catalyst can also degrade over time.
That makes sense. Thank you. Okay, what else do we have? So what are the potential applications of on-site electrosynthesis of hydrogen peroxide?
Yeah, so one of the applications I mentioned in my slides was for water treatment application. So that's kind of like the current commercialized companies focusing on that now. But there are other applications for this. For example, the sanitization, on-site sanitization, or hydrogen peroxide itself is actually a valuable chemical that is applied to many different industrial processes. So in fact, for example, for the paper bleaching, the company of paper bleaching has to transport hydrogen peroxide. So if they can produce hydrogen peroxide on site, they don't need to transport it from somewhere else.
Wonderful. Yeah, that could be very significant.
Exactly.
Alrighty. How do you envision the future of computational and digital chemistry in material discovery?
I think it's only advancing. It will be advanced more and more in the future, given that we have now much more powerful supercomputers and high performance computing machines. And as these technologies advance, the computational and digital chemistry advances as well. We now have this emerging of the AI and machine learning into digital chemistry, which is also helpful and also helping toward advancing catalyst discovery more and more.
Wonderful. Thank you. And I imagine your answer to that question will be totally different a year from now as things keep
Exactly.
changing and developing.
Absolutely.
Alrighty, I do have one more question, but before we get to the kind of the last question, just once again, anyone from the audience, if you do have any questions, this is a great time. And if you think of something later, just please reach out via email and we can follow up. But if not, my favorite question to always ask in these talks is, what is the most surprising or unexpected thing you discovered in your research?
That's a good point. So one of the so I can give you an example that I mentioned in my slide. So when I was working on electrosynthesis of hydrogen peroxide, one of my very first project was working on this single or isolated active sites. And so when we searched for materials, we also included mercury in our search. And we identified platinum mercury as our star catalyst, and it is our benchmark catalyst today, even though it's made out of mercury and it's not commercialized because of that. it was very surprising to see when you think out of the box and don't exclude everything, you can get to fascinating results.
That's wonderful. Thank you. I always find it really exciting when you discover something new and unexpected, and that's how science progresses. Um, so a huge thank you to you for sharing your expertise and your knowledge with all of us this evening. What a gift. And a huge thank you to all of our attendees. Thank you for taking the time out of your evening to join us today. And like I said, if you do have any questions, please feel free to reach out. We're always happy to follow up with you. And we look forward to seeing hopefully many of you again at our next Café Scientifique in 2025.
Thank you
Okay,
so much. That was wonderful. Really appreciate it. Thank
wonderful.
you.
Have a good night, everyone.
You too. Bye.